Now the t-distribution is very much like the normal distribution in that it is essentially bell-shaped and it's symmetric about the mean. However, whereas the normal distribution is just one curve, it's the bell curve, this is a family of curves, okay? And each of those is determined by something called the degrees of freedom. The degrees of freedom is 1 less than the sample size, 1 minus n minus 1. And it comes from, technically it's the number of free choices left after a sample statistic is calculated. We will not actually need to worry with why that's the degrees of freedom, but it is equal to 1 less than the sample size. So you'll use it quite regularly. You'll use it in t-distributions, chi-squares, f-distributions that we're coming up on. So just remember degrees of freedom is 1 less than the sample size. Now the total area under the t-curve, just like under the bell curve, is 1 or 100%. The mean, median, and mode are equal to 0, just on the, like on the z-scores. As your degrees of freedom increases, your t-distribution approaches the normal distribution. And at 30 degrees of freedom, your t-distribution is undistinguishable from the normal z-distribution. So there is a t-distribution with degrees of freedom of 2, meaning n equaled 3. There were 3 in this sample, little tiny sample. If we increase the degrees of freedom to 5, that curve comes a little closer down towards the x-axis, but it also rises a little higher in the middle. So the real low degrees of freedom is going to give you kind of a flat curve pretty far away from the x-axis. And then the normal curve comes down very close to the x-axis, and it comes up higher in the middle. Okay, so the tails in the t-distribution are thicker than those in the normal distribution. So your numbers, your t-values are higher than your z-values tend to be. Okay. So now how do you decide? Do you use a normal distribution or a t-distribution? Well, we have this lovely little chart. Your first question, is your sample size at least 30? 30 is the magic number, greater than or equal. If yes, then you use your normal distribution with your margin of error equal to critical z times sigma over square root of n. Or if you don't know sigma, you can use s as long as your sample size is at least 30. If you do not have a large sample size, you still have a chance to use normal. Is the population normally distributed? If yes, then is sigma known? If yes, then you can still use the normal distribution. Okay? So if you have a normally distributed population and you know the standard deviation for the population, then you can use the normal distribution. If not, if your population is not normally distributed, then you cannot use the normal distribution or the t-distribution, okay? So if your population is not normally distributed, you cannot use either of these and you're off doing something else. If alpha is not known, or sigma is not known, then this is where you use the t-distribution. So long as your population is still at least approximately normally distributed, that's when but you don't know the population standard deviation, that's when you're going to use the t-distribution. And the margin of error is critical t times the standard deviation over the square root of n. And you'll use n minus 1 degrees of freedom. So see how the formula is almost the same. If you're using almost the same formula for the margin of error, instead of z, we use a parameter called t. And the ALEKS calculator will give that to you. And S is the sample standard deviation instead of the population standard deviation, and still over the square root of n. So for a t distribution, use the calculator provided to solve the following problems. So on all of these in the confidence intervals, you'll make good use of your ALEKS calculator. It's much better than just a regular calculator because it'll do the statistics. It'll do all of your probability stuff. So consider a t distribution with 3 degrees of freedom. Compute the probability that t is less than or equal to 1.21. Round your answer to at least 3 decimal places. So see this key here kind of in the middle of the calculator. The probability that t is greater than something, okay? That's the one that's going to give you the probability is the area under the curve, and it'll be this shaded area. On all of these calculator functions, what you're going to get out of it will be the shaded area. When you hover over that key, it'll show you what it's going to give you. However, on this problem, you want t less than or equal to 1.21, but the ALEKS calculator only will give you greater than. So essentially, to get the other half, you're going to subtract from 1. So see how here in the calculator, I put 1 minus the probability of t greater than 1.21. It gives you a place to put the degrees of freedom in. And then once you calculate that and hit equals, then it will give you 0.844. Okay? Okay. So this is the other half of that same problem. Consider a t distribution with 23 degrees of freedom. Find the value of c such that the probability of between negative c and positive c is 0.90. This is essentially a confidence interval. So they're asking you to find essentially the confidence interval for a 90% confidence level. Okay, because see that's what the concept of a confidence interval is. So here's 0.90 in the middle. So alpha is 0.10. So t of 0.10 over 2 is 0.05. And then your degrees of freedom, it gives you a place to put it right into the calculator. So t of 0.05 with 23 degrees of freedom is 1.714. So that is C. Okay? Because that 0.05 is this area here down at the bottom. So this area down at the bottom, 0.05, and the area up here at the top, 0.05 here, is cut off by this number C. Okay? So there's your calculations to find essentially the endpoints of the confidence intervals.